Let's talk about oscillations. Thanks to Wikipedia for the picture. Wikipedia, free use for anyone, I think. It's for educational purposes. Oscillations, or SHM, which stands for simple harmonic motion. Simple harmonic motion. All right, so we're going to talk about the motion of things like pendulums, or merry-go-rounds, or swing sets, or anything that repeatedly repeats its motion over and over again. So if you look on the right here, we created ourselves a little setup with springs and weights, and we got the weights oscillating up and down. Okay. So what we're going to look at is what conditions are, well, first of all, we'll talk about certain aspects of this, but then we're going to look at what conditions are necessary in order to create simple harmonic motion that sort of mimics the way that objects move around circles, okay? Because there's objects that might appear to be SHM, simple harmonic motion, that actually aren't, okay? So what requirements are there to set up proper simple harmonic motion, okay? Now, I want to change colors. Gotta do what? All right. So what we did was we took our weight here, we pulled it down, and we released it. We found that it oscillated up and down somewhere within this bounds. Okay, so there was the low bounds and the high bounds. And we're going to call the difference between these two x. Okay, so that's x. There's a time associated with one complete oscillation. Okay, so one complete oscillation involves going all the way down and coming all the way back up. So that takes some time. Okay, and we're going to define how all of these terms sort of relate to each other and what we mean when we say them. So the first thing we're going to talk about is exactly what we mean when we say SHM, or an oscillation, and that is simply a repeating motion which has a constant period. Okay, so what's a period? Well, a period is the time it takes to go through one complete oscillation. That's the period, always measured in seconds. Not always measured in seconds, I shouldn't say that, but the SI unit for period would be seconds. Okay. So some terminology, some terms. First is cycle. When you look at an object moving up and down, really you don't, the word cycle doesn't necessarily jump to mind. But when you look at the relationship between an oscillating object that's, you know, just oscillating, say, in the y plane here, and then look at where the circle is in the y plane, okay, you can kind of connect between the vertical up and down motion and the cycling of your point around this circle, okay? You know, so if we were to imagine this as a unit circle, okay, well then we can define different points around here, and you can see how motion around a circle and motion up and down in the y-plane would mimic one another for SHM. So a cycle then is just one complete oscillation. Okay, one complete oscillation. We would have an equilibrium position. In this scenario here, equilibrium would be right in the exact center of the motion. Okay, it's probably a little more common sense to talk about this in terms of a wave. All right. So the other thing we're going to do is we're going to talk about waves. Okay. So you can imagine as this goes up and down, someone puts like a pencil on it, and they take a piece of paper and they slide the piece of paper from left to right. Okay, so in this direction. Well, this thing would tend to draw out like a sinusoidal wave as you pulled it apart. Okay, as you pulled it this way. Well, real life waves also do this. You know, if you took a rope and you started to whip it up and down, you would get waves, and right in the dead center of that would be considered the equilibrium position. Okay? So we'll call it dead center between max and min amplitude. We'll get to amplitude in a second, but it probably makes good sense to just draw a couple of pictures of where equilibrium positions would be. So let's say instead of a spring pendulum, you have your classic rope pendulum. All right, that's oscillating kind of like this. Okay, so different positions here. We would consider the equilibrium position to be where it remained at rest. All right. On a spring pendulum, it's possible that you might not have rest exactly in the middle, but that's where equilibrium would be. Okay. So equilibrium would be right in the middle. So if you're going up to here, down to here, that's our equilibrium position. Okay. And if we have a rope or a spring, okay, and we put a wave into it, the wave looks like that. Okay. Well, this medium, whatever medium that wave is traveling in, okay, once the wave has passed, it will return to its equilibrium position. So that's what we mean when we say equilibrium. It can mean different things in different cases. In the case of this phase space drawing, since this doesn't actually represent real motion, you know, there's not really a true equilibrium position like there would be if this ran out of steam and eventually kind of came to rest, kind of sort of right in the middle. Okay, the next term we're going to cover, we're just, sorry, behind the scenes debating whether or not this would come to rest at equilibrium. And I think as long as this spring obeys Hooke's law perfectly, I think it would come to rest directly in the center. But I don't know if I want to stake my reputation on it. I think it would. Definitely theoretically, I think it would. I don't know if it would for sure in actual practice. But let's not get bogged down. Let's go over to amplitude. So amplitude is just the maximum measurement or displacement from equilibrium. Okay? So you have to be careful. Amplitude is not this whole thing. Amplitude is displacement from equilibrium. Okay? So that's the amplitude. One way here is the amplitude, and one way here is the amplitude. So max displacement from the EQ or the equilibrium position. Okay? Period. So period and periodical are related, right? It's the time it takes for, in this case, for one complete cycle or oscillation. Generally measured in seconds. All right? And if we can measure the time it takes for one cycle, we should also be able to measure the number of cycles happening per unit of time period, per unit of time. So frequency is related to period. In fact, it is the inverse of it. And this is the number of cycles per second. Okay, so number of cycles per second. The symbol for period, by the way, is T. Symbol for frequency is F. So if we want to write in a little equation, we could say that frequency is equal to the inverse of period. And that would also therefore be true. Okay, so it's kind of an important thing to remember. And just as an example, let's say I want a different color. Example, let's say your period is 2 seconds. Okay, period is 2 seconds. So let's say it's a little kid on a swing set, right? They push them, they go away, and then they come back, and that took 2 seconds. Well, every second, how much of a complete cycle do you get? You get half, right? You get half a cycle every second if every cycle takes 2 seconds. The unit for period is seconds. The unit for frequency is hertz. Hertz, okay? And hertz is just something happening periodically and how many times it happens per second. So the unit is just simply per second. So you could apply hertz to anything that's happening periodically. Anything that's periodically repeating would have a frequency. Just as an aside before we move on, there's a question about connecting a swinging pendulum to cycles or to circular motion. So here's how I'll do my best to explain that. Let's say our pendulum is swinging kind of like this. We're kind of trying to show it at like a bit of an angle. So we're looking at it sort of from the side. So it's going back into the page and then kind of out towards us. And then let's say we're pulling paper along this way. Okay. As the paper comes along, if there's like a light pointing down onto the paper as this oscillates back and forth, it's going to churn out, okay, a sine wave as it oscillates back and forth. And then if you want to connect that to a circle, okay, here's your pendulum, your swinging pendulum, going like this, side to side, okay, and above it, we'll draw ourselves a little circle with the diameter equal to the max outward swing of these things. So those points there. And as the circle cycles around, okay, we just imagine this is now at its max out and it starts to move back in. The x coordinate or the x distance from center between these lines is always going to be the same, right? So if we just look at how far out we are from center, you're always going to find that they, you know, kind of line up with each other. All right? So there we go. We're connecting the swinging pendulum, the bouncing pendulum, circular motion, and waves all together here. So it's possible that we might also talk about angular frequency from time to time. Angular frequency. This requires that we bring in the concept of radians. Okay, so I just threw a little animation in here in case you're unfamiliar with what a radian is. But what a radian is, you know, in short, you can kind of watch this go through, but basically it's how many times the radius of a circle will fit around the outside. So we know from, you know, our younger days that there are 2 pi radii, in this case rad, equal to 1 circumference. That's what a radian is. So angular frequency, which is measured in W's, is equal to basically it's just equal to how many rads are going by every second. Okay, how many rads per second are we doing? All right. So just to clarify this even further, okay, the frequency, oh, jeez, the frequency, that was a little hard to understand maybe, but the frequency is, okay, the frequency is how many times we go right around every second. So what that also means then, if the frequency is how many times we go around every second, like full oscillations per second, well, we go 2 pi radians every second, right? Let's divide by time. So frequency is 2 pi over t, okay? But that's a special frequency. We don't call it f. Oh yeah, we do. Sorry, we do call it f. Yes, that's normal frequency. Normal frequency is 2 pi over t. So therefore, angular frequency is just 2 pi times frequency. Okay, because this is regular frequency, right? How many times per second it's happening, and multiply by 2 pi, and then you get W. Okay, so it'll be a smaller value. W will be a smaller value. I'm sorry, W will be a larger value than frequency, which makes sense because you have to go 2 pi radians for every 1 revolution. There's an R in here. Sorry. 2 pi R over T. My bad. So, just discussion behind the scenes again. This might be confusing. Maybe don't even worry about this for now. Just think about making sense of this. All right. So, what it's trying to say is how many radians do we cover every second? That's our angular velocity, or sorry, our angular. Yeah, I guess angular frequency. Okay, how many radians per second do we cover? If we know a normal frequency, like let's say it's 2 hertz, we're going around 2 times per second. Okay, but every time we go around once, we go around 2 pi radians, right? 2 pi radians. Go around 2 pi radians. So the angular frequency of 2 hertz, okay, is going to be W equals 2 pi, right? Because for every hertz, we got to go around 1 time. Times 2, so 4 pi is our angular frequency, which is the equivalent of 2 normal hertz. Okay, so it's 4 pi would be our angular frequency.